Welcome to this fifth part in this video tutorial series about the Opengl API. In the previous part, we worked with translation and this was our output. So in this part, we're first going to learn about the third dimension and then I'll show you how to set up a projection so that you can view your 3D world. So first thing, we need to make some changes to the program that we currently have here to avoid any confusion in the things that we're going to learn today. You have to comment all of the animation code. So just comment all of this code and also remove any translation that you were doing. And I'll also draw this square in a single color, so I'll remove all the color commands except the first one. So now you can build and check this if you've made the changes right. So this is it. So now let's talk about the third dimension. So if you have worked with the 3D coordinate geometry, you'll be quite comfortable with the things that we're going to learn now. If you've not, it'll take a bit of time before you get experience to it. So you just have to be patient, and it takes time getting used to the 3D coordinate system if you've not yet worked in the third axis. So this is the 3D coordinate system. It has x, y and z axes, and the third axis is the z axis. Like a square is a two-dimensional object, but a cube is a three-dimensional. Now it has a third dimension, which is in addition to length and breadth. Like a square has equal sides, and then there's the height. So that is the third new dimension. So similar way here in the 3D world that we have inside our API, we have the x-axis, then we have the y-axis. Now these lie in the plane of your screen, so this is towards the right side. Sorry, this is y-axis, and the y-axis points upwards, and the positive z-axis points outwards. So this is the positive z-axis, and into your screen is the negative z-axis. So all you have to do is remember that the coming out of the screen is the positive z-axis, and going into the screen is the negative z-axis, and the x and y-axis will be as usual as we have used so far. Now you have to use 3 coordinates to specify a point inside the 3D world. So like first you have to specify the x position of a point, and then you have to specify the y position of the point, and then you have to specify its depth. Like you have to specify a point and then its depth, which is the z coordinate. So it'll lie somewhere in your 3D world. So that is how you specify a point inside the API. You need 3 vertices. Now if you look at the function calls to specify the vertices, we use the vertex2f function, which specifies 2 coordinates for each point. So instead now we'll use the vertex3f function, which also allows you to add an additional argument, which is the z coordinate. Now this what I just did here didn't make any difference, because if you use the vertex2f call, the vertex is always specified in a 3D format, but if you use the vertex2f function, the z coordinate is automatically set to 0 by your API. So all the changes I made here didn't make any difference. So I can do this to all of these, because now we're gonna need to use the z coordinate as well, but I'll initially set this to 0 here. This will not make any difference. If you want to check, you can build it on your application and see that it doesn't create any difference really. So now you know how to specify a point inside the 3D space. Now the next thing is viewing your objects inside the space. Now just as you specify, just as you drew a square here, now if you look at the geometry and map this geometry onto your screen, onto the coordinate system, you'll find that it represents a square. Sorry, I'll draw it in a different color. A square which is placed at the origin. The center of the square is at the origin. This is the place the square is at. Now you can in a similar way, using the coordinates, you can specify various objects which are located at different points. So each object can be located using the set of 3 coordinates that you have to use here. So now the next thing is that you have to specify a particular criteria which will tell the API how the objects inside the scene are viewed. It's not like you have every object inside the scene. The user cannot see all the objects at a single time. So that is specified using the projection. Now projection will determine which how the scene is viewed, and which objects are clipped inside the screen and which are clipped out. So now, to get a basic idea of the projection, you need to just imagine that you're standing right here at the origin, and now into the screen is the negative z-axis, which is this side. So imagine you're looking into the screen, means you're looking to the negative z-axis. So now this will be the range in which you'll be able to view. So this is actually called a view frustum. Now you can see the rays diverging. This is how a human perceives the images which are in front of him. This type of projection, in which the rays diverge, is called a perspective projection, because in this case, if you have 2 objects lying on the z-axis which are of the same size but are at different distances from the observer, the one which is closer will appear bigger to the observer, and the one which is further away will appear smaller. This projection is called the perspective projection. Now if you want to have a better look at it, these diagrams will help you understand. Now this is the orthographic projection which we used in the previous part. We do not need to worry about that right now. We'll study about it in detail in the upcoming parts. So let's first have a look at the perspective projection. So this is the observer and this is the negative z-axis. This is the observer, or you can call it a camera. It is always centered at the origin and it is always looking towards the negative z-axis. Now in OpenGL you need to specify some parameters which determine this frustum. Now frustum is a pyramid which has been cut off from a place. So you can see this is our view frustum, this much. The near clip plane and the far clip plane included, and this inside area comes inside the view frustum, and all the objects inside this are visible. You need to note that the objects which are nearer than the near clip plane will also not be visible. The objects which are nearer than the near clip plane will also not be visible, and the objects which are farther away will also not be visible. Only the objects lying between these. And if an object like this green ball lies out of the view frustum, it will also not be visible. So only the objects present inside this frustum will be visible. So like this yellow ball and this red ball. Now the yellow ball is more closer to the observer, so it will appear bigger when it is projected. So now you can imagine the near clip plane as a screen onto which all of the scene inside this frustum is projected. You can imagine it like this. All of the scene is projected onto the screen, and you're standing here and now you're viewing this screen. So this is you can imagine this as a viewport of that is present inside your window. So all of the scene is projected right here. Now in OpenGL you need to specify this view frustum, and to use it you need to have certain parameters. Like you can see it'll have certain width and height and certain angle here, so you need to specify that. And so first we'll start specifying the projection. So if you go into the reshape function, you see this glue author 2D function that we call to set up a temporary 2D projection while we working with the two-dimensional objects. So we use this function. We first changed to the projection matrix, and then we made changes to the projection matrix using this function. So similar function used to set up a perspective projection is glue perspective. The first argument is the field of view angle. Now what is the field of view angle? I'll explain it to you here. So you can see this the angle between these two lines, or these two lines, this is pretty much the same thing. This angle is called the field of view, or FOV in short. Now you can usually keep it to 45 degrees or 60 degrees. That is quite usual, and it appears lifelike. So I'll use 60 degrees for field of view. And the next argument is the aspect ratio. Now aspect ratio is the ratio of this width and height. This is same throughout the frustum. because this frustum is uniform. So this ratio is same throughout, and you need to specify this ratio. Now we are using a square window in our program, so it'll be convenient if you keep the ratio 1, because this frustum should also have a square base. If you if the dimensions do not align, like you have different ratio for your viewport and you have different ratio for your view frustum, so the scene might appear stretched out in a certain direction. So that is not quite ideal. So you've always got to keep the ratio of the window equal to the aspect ratio of your projection. Now the next argument is the z near and z far distance, the next two arguments. So the z near distance is the distance of this near clip plane from the origin. This distance will always be positive, the positive distance from the clip plane to the observer, so we'll keep it 2. And the far clip plane, you can keep it as large as you like, but it'll be convenient to not to keep it too large, because if too many objects are drawn inside your scene, that might result in performance issues of the computer. So z near 2.0 and z far I'll keep 50.0. so any object drawn behind this far clip plane will not be visible. So now I'll use a diagram to demonstrate what was going on here. So let's suppose this is our view frustum. Now I cannot actually draw a 3D frustum, so I'll just use a triangle. So this is the near plane and this is the far plane. So these are the negative coordinates here, but the distance is always positive. So the near plane and far plane distance is always the positive distance from the origin to the plane. So this was 2 units, so this point is -2, and this point was the far plane distance was 50 units, so this point is -50 on the z-axis, -z. So all the objects between this region will be visible. Now this is a 3D frustum, so this is a 3D region in which these are visible. So you can draw any object which lies between these frustum and they will be visible. Other objects will be clipped out of your screen. And the object that we currently have here, if you map this geometry onto the coordinate system that we have here, it will be a square which is drawn at the origin. So you can see it does not lie inside the view frustum, so it will not be visible right now. So for it to be visible, you have to translate it to a point which lies between the near and the far clip plane. But for now, let's just verify that if this is visible or not, if it is being drawn at the origin. The object is not visible. And now if I translate it to a point which lies between the near and the far clip plane, like -15, now it should be visible. So now if I build and run the program, it will be visible. And now you should know that this is a perspective projection, so the objects which are farther away will appear smaller and the objects which are nearer to the observer will appear bigger. So you can just experiment it right now. So this is our object at -15, and if I draw it at a point let's say -5, so this is nearer to the origin, so this is nearer to the observer, so it should appear bigger now. So this will be verified by the output of the program right here. You can try setting the distance to various values and you can check if this is working or not. So this is definitely bigger than the output we had in the previous part. So the object is not changing its size, it's just changing its distance from the observer. Now you can actually use the animation code that we had in the previous part to translate it on the z-axis, just like we did on the x-axis in the previous part. So now the range of the variable, it'll go from -5, let's say, to -15. Though the variable is called x position, but we'll use it for the z-axis, so this will be x position. So now if you build and run this, you should get an animating effect that the object is going away from you and then it is coming nearer. So another thing you need to know, that we cannot yet work with 3D models, like you cannot draw a cube, because if I draw a cube, only its front face will be visible to you, and the and the body of the cube behind that will be hidden, so it will again appear as a square. So before we can draw a 3D object, and if you want to view it from different angles, you need to first learn about rotation. So we'll learn about rotation in one of the upcoming parts, and then we'll draw 3D objects, and then we'll be able to view it from the different angles. So for now we'll just work with a 2D object inside 3D space. So we had the output that we needed. So this is how the perspective projection is working. You can try experimenting with multiple objects inside your screen. You can try animating them. So you can also try drawing the geometry of the cube at a different position. That is really up to you if you want to do that, although we'll do that in one of the upcoming parts. And another thing we'll need to learn about here will be the depth buffer. That is actually a hidden surface removal, like the objects which are behind certain objects will not be visible because the object in the front hides the objects behind it. So that is actually not how OpenGL works by default. It does not know that which objects it has to hide and which it has to show. So we'll learn in the next part how to enable depth testing, which always checks the objects which are in the front, and it always hides the objects which are behind certain objects. So that will be covered in the next part, and with that we'll also cover the orthographic projection in the next part, and after that we'll start with rotation and we'll draw the 3D objects. So that was all for this video, and I hope to see you next time.